Okay, so these points are called nodes. Wherever, see, for this value of kx is equal to pi by 2, 3 pi by 2, and if I solve it by putting k equal to 2 pi by lambda, we get the value of x is lambda by 4, 3 lambda by 4. We get that the displacement is maximum. Okay, so this point, for this kind of points, oscillate with maximum possible amplitude, and these points are called the antinodes. So we got the concept of nodes and antinodes. Node displacement, zero displacement, nodes, and maximum displacement, antinode. And it depends on some, for some position, we get these points. Okay, so if I look at, look at the picture over here, the figure over here. So you can see these points are antinodes. Obviously, this is the maximum amplitude region, right? So the maximum amplitude, this is antinode, right? And then this is antinode. And if I draw a line over here, this is the equilibrium line. Okay, this is our coordinate, which is not drawn over here. If I draw this line, so this line will correspond to zero displacement, right? This is y equal to 0 line. I'm drawing this y equal to 0 line, right? So you can see that these points, okay, we have this wave intercepts over here, y equal to 0 point. So this point will be a node, zero displacement. This point will be a node, and so on. So the property of a stationary wave, it is different from the traveling wave or other waves we know. So it does not move through medium, and energy is not carried away from the source. Okay, so the whole energy is confined to some region. Oh, it's like oscillation, right? And the amplitude of stationary wave varies from zero at a node to maximum at an antinode, and that we have shown it in the previous calculation. Okay, so going to our next slide. So the calculation over here is same as we have discussed so far. Y equal to a sine kx minus omega t, y2 equal to a sine kx plus omega t. We add them up, okay, and we apply the trigonometric formula over here, and we get this formula, the bold, you can see the formula in bold letters over here. Okay, so this is our formula. As you can see, the third bracketed term represents the amplitude, which is obviously the space dependent part, and you can see this part is the oscillation part, cos omega t part. Okay, so the point is that we have already discussed about this amplitude part. Now let's discuss about the oscillation part. So you can see that depending on the value of t, that what is the time we are considering, at what time we are observing the wave, okay, we will get we can get some value of cos, because cos value also varies from 0 to plus minus 1. Okay, so you can see that initially when time t equal to 0, so the two waves are in phase, right? And the result is a wave, this cos t equal to 0, cos equal to 1. So this is a wave that is twice the amplitude of individual waves, right? So twice a is the amplitude. Okay, and if time t equal to t by 2, capital T represent the time period there. Okay, so time period of the waves. So if this, we are observing it at t by 2 time, and you can see that they are in phase. So if time is equal to t by 2, then also the waves are in phase. So we can write down that if we are observing it at t equal to n multiplies by t by 2, then when n is 0, 1, 2, 3, the waves are in phase. And for other times, okay, when they are out of phase, that means the two waves are pi radian out of phase. Okay, so the resulting wave will be equal to 0. right? So you can see if t is equal to pi by 2, so omega t is equal to pi by 2, right? So we will get cos pi by 2 is 0, and the resulting wave, you can see that y will be 0. So for one condition, this condition, in phase condition, is for when cos omega t is plus minus 1, and the second out of phase condition is for cos omega t is equal to 0. And if I solve this, we get the time, as this, okay, where obviously n equal to 135. Okay. So this is the point, and if I represent it, graphically, it is a bit easier to understand that what happens. You can see that this is this graphs, actually you can see over here. So this blue, there are two lines over there. Where is this? Okay, this blue and red lines you can see over here. So blue and red line, they represent the two superposing waves, okay, and the resultant wave is shown in black. Okay, so yes, so I hope you can see this. Okay, so this is, can you see this picture? Okay, and for different time, time, t equal to t by 4, capital T by 4, capital T by 2, 3/4 t, we are getting this kind of superposing waves. Okay, so the one point, you can see these things. Okay, so if you note the black lines for each graph over here, if you see the black lines, you can see for some positions it is marked in your graph that this is x equal to 3. You can see this is x, the x direction. So x equal to 3, this is x equal to 6, this is x equal to 9. For every graph, this, whatever the time we are taking, for all time, for all value of t, we get this x equal to 3, x equal to 6 and 9, these points actually correspond to zero displacement. Okay, you can see whatever the time is, zero displacement. So these points are called the fixed points, or the nodes. Okay, and the points where the oscillation is maximum are called the anti-nodes. Okay, so why we get these points, in space at nodes, why it is always zero displacement? Because the amplitude part, if we remember that the amplitude part, you can see over here twice sine kx, right, this part. So the amplitude part, it is zero for this positions. Okay, so for that kind of graph, the graph we are considering, okay, for x equal to 3, 6, okay, represents these positions. Okay, x equal to 0, lambda by 2, lambda 3, lambda by 2. So whatever the time may be, so the displacement, actual total displacement, is always 0. So this is the time representation. So as we know that time, and both time and space representation of the graph. Okay, so I hope I want to illustrate it in terms of time and space as well, how this displacement changes. Now, this is the thing that we have already discussed, that when for which value of sine kx we will get nodes and antinodes, and what are the values of x's. So we already discussed that x equal to 0, lambda by 2, 3 lambda by 2, these positions are for nodes, and x equal to lambda by 4, 3 lambda by 4, 5 lambda by 4, this position represents antinodes. Okay, maximum amplitude. So we are not going to discuss this slide anymore. So you can see over here, so this is this is same thing representing, this is a standing wave, how the standing wave looks like. Okay, and you can see that this red dots obviously represent the nodes, okay, zero displacement, and this blue dots the antinodes. Okay, uh, moving on to that, uh, you know how we can generate these stationary waves in laboratory. Okay, so so there is, you can see over here there is a string. Okay, so this string is this is there's a stretched string over here, and we have fixed a frictionless pulley at the end, and we have applied this hanging mass over there. So this hanging mass provides the tension in the spring. Okay, so this string is stretched now. Okay, we know the we have already discussed stretched string, and what is the wave. If we pull this in transverse direction, one wave will be propagating, and we know what is the velocity of it. So this thing we have discussed in our previous class. So this thing, this thing okay, so this is how this is a setup. And if I this is a vibrator over here, so we can use some electrical vibrator to induce some displacement here. Okay, and one wave will be propagating through it, and at these two points, you can see these 2 points, the 2 end points cannot have any displacement because they are fixed ends. Okay, they are fixed ends, so these 2 points will act as nodes. Okay, so these waves, when they propagate through this spring, they will reflect back from this end. Okay, and they superpose on each other, and some stationary waves will be formed. So this is how this stationary waves are formed, and we know that the velocity of the wave depends on the tension and the linear mass density. That means mass per unit length. Okay, so are you people there? Are you people listening?
Yes, ma'am.
Okay, so if you have any problem, you can ask me. You can stop me and ask me. Okay. Now about the fundamental frequency. Yes, this is a better view over here. Okay, it's a better representation. So this string we are considering over here, this length we have taken, this between these 2 fixed points. Okay, so we have taken the length is capital L. Okay, so you can see that how the waves, so there will be some modes. Okay, so the next thing we are going to discuss is about modes of these stationary waves. So you can see that the only condition here is the endpoints we are considering. The endpoints will behave as a node. Okay, so that's my condition. So when this can be so, okay, so suppose a stationary wave is formed like this. Okay, you can see this first figure over here, the stationary waves. Okay, so you can see that this is this is the total wavelength, this one, and then goes up. So this is called a full wavelength. So this position is called the half wavelength. So the whole length represent half wavelength, right? So this can be one mode. Okay, if we have to apply the condition that 2 fixed points behave like a node. So if I apply this condition, lambda by 2 is equal to L for the first figure. So we get the wavelength is twice L, 2 by 1 L. So it is written like this because we want to convert it in general form. So that's why it is written like this. So lambda is equal to twice L. So there will be one frequency associated with this particular mode, right? And suppose the frequency is F1. Okay, so F1, you know, the frequency is the velocity of wave V is equal to nu into lambda. No, not nu. Here it is represented by F. So F into lambda gives the gives the velocity. Means frequency into wavelength gives you the velocity. So if I want to calculate the frequency, it will be velocity by wavelength. So you can see here, so it is written that velocity by lambda 1, and we have already seen that the value of lambda 1 for the first node is twice L. So V by twice L is our first frequency, and the speed of v, obviously the speed of this wave, and it is root over t by mu, t by m. We have already derived this, okay, in our previous class, velocity of this wave. Okay, so this v by twice L gives you the frequency of the first node, and this is called the fundamental frequency. Okay, so this n equal to 1 mode gives you the fundamental frequency. Now suppose we can also have this kind of mode over here where the displacement looks like this. Okay, so it does not hamper our only condition, that two endpoints behaving like nodes, and for this kind of representation we can get this kind of waveform. We can get one extra node in the middle, right? So you can see it's a total wavelength over here. So here we can write down this lambda 2 is equal to the total length of the string. So it is 2 by 2 L. Okay, so that's how it is represented. Okay, so you can see that if I calculate the frequency for the second mode, it is F2 is equal to velocity by lambda 2, velocity by wavelength. So velocity by wavelength is L. So if I compare this equation with this, we get that this frequency is actually twice the fundamental frequency, right? So this is our fundamental frequency, V by twice L, and we get V by L. So it is twice F1, twice the fundamental frequency. So similarly, if we go on, now we have this waveform. If this type of waveform is created, we can see that two extra nodes arises in between the fixed ends, right? So this is n equal to 3 mode, and we can see this 3 by 2, this is 1 lambda, and then this is half lambda. So total is 3 by 2 lambda. So 3 by 2 lambda is basically represent the whole length. So we get the value of lambda over here, and similarly we can calculate the frequency for the n equal to 3 modes. So similarly, if we go on, we can calculate the wavelength and frequency of the nth mode. Okay, and this is represented by here. You can see that lambda n represent the nth mode wavelength, and it is given by twice by n. As you can see, 2 by n, 2 by 1, 2 by 2, 2 by 3, 2 by 4. So it is basically 2 by n for nth mode. Okay, so moving on, here is a better representation. It's like a chart over here that you can get that what are the modes of vibration of strings. You can see this is our fundamental, or it is called the first harmonic. Okay, so F1 equal to V by twice L. Okay, this is a fundamental frequency, and the structure is also given here. You can see how many nodes, how many antinode is there. Okay, so it is given over here, so you can just compare with different modes. And the second frequency we get, we call it second harmonic, and so on, third harmonic, fourth harmonic, and so on. So it goes on. So if it is fourth harmonic, so it is fourth time, 4 into f1. Okay, so that's why it is called fourth harmonics. That means 4 times the fundamental frequency. So I hope you understand, up to this, the modes of the stationary waves, what I'm trying to say. Do you have any question or doubts over here?
No, ma'am.
Oh, okay, so moving on. So there is a comparison here that what is traveling wave and what is stationary waves. Okay, so these points we have already discussed. So I don't need to explain them, but I have to emphasize the points. First, this is traveling wave. It carries energy, obviously, and standing wave because it is confined in space, so it does not carry any energy, and it has a fixed amplitude for traveling wave, and we know the amplitude is space dependent and varies from 0 to twice a, and it is not confined to given space, and it is confined to given space to walls. Okay, so two fixed ends, okay, maybe two walls or maybe two ends of the string. Okay, so it depends on what system you are considering where the stationary waves are formed. uh, the traveling wave, it can have any frequency. Okay, so from 0 1 1 1.2 1.5, so it can have any frequency, but the frequency here is quantized. Why this is quantized? As you can see over here, that this f1, the first frequency it can get is v by twice l, then this is v by l and 3v by l. So any intermediate value of frequency this stationary wave cannot have. Okay, so if we want to say, okay, no, we want to take a frequency of v by 3l. Okay, so this cannot happen. It can only have this kind of frequency. And quantized, obviously, the meaning of quantized is discrete, not continuous. So continuous means it can have any value, and discrete means some discrete values it can have. So no intermediate value of frequency. The Then what is the wavelength, what is the distance? So when this the description of wavelength is the shortest distance over which the waveform repeats itself, and here the definition is like 2 times the distance between two nodes or antinodes. Okay, so and then the last obviously is the mathematical representation, how traveling wave is represented and how the stationary wave is represented, okay, mathematically. uh, so that's all for today, and I hope that I see that I have some time over here. So let me, I want to log in from my other device so that I can do some board work over here. Okay, so I will continue this discussion. Okay, 1 minute over here. So I want to continue this discussion, uh, uh, this discussion, and discuss about what is the eigenfrequency and eigenfunction of this kind of stationary waves. But for that I had to log in from my other device. Okay, so can you just hold on for 2 minutes so that I can do that? Okay, just hold on for 2 minutes. Okay. Can you hear me and see my screen?
Yes, ma'am.
Okay. Um, yes. Yes. Okay. So we were discussing about stationary waves, right? So stationary waves, and we know that this is how there is a fixed end over to fixed end at x equal to 0 and x equal to L. Okay, and then the stationary waves are formed like this. Okay, so this is the second mode, right? N equal to 2 mode I have drawn over here. Okay. uh, so uh, due to how this is so we have already discussed that how it is generated. Now in our previous class we have discussed the uh, general solution of this waves. Okay, so if you remember that we have this, right? You can see over here we have general solution of wave equation, method of separation of variables. Okay, so this is our wave equation over here, and we have done the method of separation of variables. We have applied this method and we got this equation. You can see the last equation over there. This is our final solution. So I told you last day that for different kind of systems, okay, different kind of waves, this kind of the C1 C2, the value of D1 D2 will change and we will get the solution. So now we are going to apply this general solution to our stationary waves problem, and we want to see that what kind of solution we get from there. Okay, so one solution we already know how the stationary wave looks like, what is the mathematical representation of stationary wave looks like. So how we get this? By superposition of two waves, right? Y1 plus y2 is equal to y, and we do the trigonometric thing, apply the trigonometric formula, and we get the solution. Now we are going to see that if we can get the same solution, using the general solution of our wave equation. Okay, so let's do that. If you have any question, just stop me and ask the question over here. So first of all, let me write down the general solution of wave. Okay, so in the last class, this is the general solution uh, of stretched string. Okay, and the solution was C1 cos omega t plus C2 sine omega t, d1 cos omega x by c plus d2 sine omega x by c. Now it's time to write down the boundary conditions for our system. So let's see what is the boundary condition for this stationary wave. Okay. So boundary conditions. So the first boundary condition is that the displacement is 0, y is equal to 0, at x equal to 0 for all t, for all value of time. Okay, so this point always acts as a node. Okay, so this is our first boundary condition. And the second boundary condition, y is equal to 0, the displacement is 0 at x is equal to L. That means this other position, other end of the string. Okay, it will also behave as a node for any value of time, any value of t, for all t. Okay, So this is our two conditions. So first let's apply the first condition, this condition number 1. So if I apply it here, that y is equal to 0, this is 0 when x is 0. So what we will get, so x is 0 means this d2 parts, because there is a sign part over here, so this part will be 0 and we are left with d1, right? And cos omega x, cos 0 is 1. So basically d1 multiplied by this thing, right? So the first, if I apply the first condition, so for condition 1, so it is from the space part, it is d1 only, and then cos omega t plus c2 sin omega t is equal to 0. Now, if this equation has to hold true for all value of t, so we can write that d1 must be 0. Okay, so d1 is 0. Let's give this equation number 1, and this is our equation number 2. Now apply the second condition for condition 2. So see, we already know that d1 is equal to 0. So we will put d1 is 0 over here. Okay, so we will put this is 0, right? So we are only left with d2 sine omega x by c. But our second condition is y is equal to 0 at x equal to L. That means this is 0 and x will be L. So d2 sine omega L by c multiplied by this bracketed thing will be equal to 0. So let's write it down. So d2 sine omega L by c multiplied by c1 cos omega t plus c2 cos omega sin omega t is equal to 0. Now, can we make this d2 0? We can always, you can say that, madam, let's take d2 also 0 as we have taken d1 0. But we cannot do so. Why? Can anybody tell me? Why we cannot take d2 equal to 0? কোথায় গেলে সব? অদ্রিজা? আরেকটু ভাবো, d2 equal to 0 যদি হয়, d1 0 হয়ে গেছে, ইকুয়েশন 1 দেখো, d1 0 আর আমি যে বলছি d2 ও যদি 0 হয় তাহলে কি হবে? রাইট, তো পুরো ডিসপ্লেসমেন্ট আর কিছু ওয়েভ কিছু পাবোই না, পুরোটাই 0 হয়ে গেল যদি d2 আমি 0 করে নিই। তো সো উই ক্যানট টেক d2 0, রাইট? সো হোয়াট উই ক্যান, সো কোনটা বাকি থাকলো যেটা আমি 0 নিতে পারি? দিস ইজ ফর all values of t, we cannot take it 0, right? This cannot be 0, so only this part left is left, right? So we have to take sine omega L c, omega L by c is 0, right? So this implies sine omega L by c is equal to 0, right? So if I solve this, that for what values of omega L by c the sine term is 0, so we get that omega L by 0, 0, it is 0 pi, right? So n pi, n pi. So where n is any integer, 1 2 3. Very good, Shandipan. So হ্যাঁ 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 হ্যাঁ, so 0, but 0th mode তো নেই, আমরা তো 1 থেকে স্টার্ট করছি, রাইট? n equal to 1 mode থেকে স্টার্ট করছি, that's why n equal to 1 2 3. Otherwise if you take 0, this omega, the value of omega becomes 0, that means 0 frequency, so it does not have any physical significance. So that's why we are not taking the n equal to 0 value, right? So moving on, now you can see that the frequency, okay, the frequency depends on integer values, 1, 2, 3. So this frequency has some discrete value or it is quantized. So for nth mode of frequency, for nth mode of frequency, so we will write this frequency, angular frequency, as omega suffix n, right? And we will write it as nc pi by l. Nothing, but we have solved. I have just solved this. Okay, n pi c by l. Okay, and then we have given nth suffix for nth mode. Okay, so this. So this is the nth mode of vibration frequency. And you can see that the vibrations, okay, the only modes of vibration that are permissible, either they are either pi by c by l or multiples of pi c by l, pi c by l. So either it is pi c by l or you can multiply any integer with it. This will give you the vibrational frequency, but no intermediate value of omega. Now we are in a position to write down the final solution. So the final node, না না না, নোট কেন, যেটা আমি দেখালাম যে যে কোনো নোট না, ধরো এরকম নিলে, ঠিক আছে। সো এইটা হচ্ছে তোমার n ইকুয়াল টু 1, রাইট? নোড হচ্ছে এই পয়েন্ট গুলোকে বলে যেখানে ডিসপ্লেসমেন্ট হচ্ছে 0, দিজ আর কল্ড নোড, and n equal to 1 is the mode, right? This is node, node, and this is mode, nth mode. Okay, so this n equal to 1 mode, and then this is n equal to 2 mode, right? It's the value of n, right? So if I take the value of n and put it here, and in the value of lambda, we will, the waveform we will get, যদি আমরা সেটাকে গ্রাফিক্যালি রিপ্রেজেন্ট করি, তাহলে যেটা আমি ড্র করি সেটা, তাহলে এটা এরকম দেখতে লাগবে। তো বুঝতে পেরেছো আশা করি। পুরো অসিলেশনের সময়, হ্যাঁ, পুরো ওয়েভের ফ্রিকোয়েন্সি এটা, ঠিক আছে। এবার ওয়েভটা কোন মোডে ভাইব্রেট করছে সেটা ডিপেন্ড করবে, তুমি কি রকম ভাইব্রেশন দিয়েছো, ঠিক আছে, তার উপরে ডিপেন্ড করবে। হ্যাঁ হ্যাঁ হ্যাঁ, না 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 না, নোড অ্যান্টি নোডের ক্ষেত্রে অন্য হবে না, এটা বাউন্ডারি কন্ডিশন লাগিয়ে পেয়েছি, তার বাউন্ডারি ওই পজিশনে নোড আছে বলে আমি এমন একটা সলিউশন খুঁজছি, আলাদা করে নোড অ্যান্টি নোড খুঁজছি না, আমি গোটা ওয়েভটার সলিউশন খুঁজছি, এবং আমার বাউন্ডারি কন্ডিশন হচ্ছে এই দুটো পয়েন্টে নোড আছে, ঠিক আছে। তো তুমি যেরকম যেরকম নোড প্লেস করবে, ইন বিটুইন দেয়ার উইল বি অ্যান্টি নোড ক্রিয়েটেড অটোমেটিক্যালি। তোমাকে আলাদা করে অ্যান্টিনোডের জন্য আলাদা করে ফ্রিকোয়েন্সি বা কিছু বার করতে হবে না, এই গোটা ওয়েভটারই ফ্রিকোয়েন্সি। দেখো না ওয়েভ লেন্থটা কিরকম, একটাই তো ওয়েভ লেন্থ, এই যে ল্যামডা ইকুয়াল টু এল, তাই তো? তাহলে এটার তো আলাদা ফ্রিকোয়েন্সি আর কি হবে? আর এটা হচ্ছে এক একটা পজিশনকে ডিফাইন করার জন্য এটা নোড আর অ্যান্টিনোড বলা হচ্ছে, হ্যাঁ। এটা জাস্ট মানে একটা টার্ম, যেটা ওই ডিসপ্লেসমেন্টটা জিরো না নন জিরো এটা বলা বোঝানোর জন্য নোড আর অ্যান্টিনোডটা ইউজ করা হচ্ছে। এই যে ফ্রিকোয়েন্সি আমরা কথা বলছি, এটা কিন্তু গোটা ওয়েভের ফ্রিকোয়েন্সি কথা বলছি, হ্যাঁ। বুঝতে পেরেছো? আচ্ছা, আরেকবার তোমরা কি করবে, যে পিপিটিটা দিয়েছি সেটা একবার গো থ্রু করবে, তোমাদের যে বই আছে আর একবার ওটা পড়বে, কারণ বইয়ের কোনো বিকল্প নেই, কোনো নোট বইকে রিপ্লেস করতে পারে না। তো বইটা পড়বে, নোটটা পড়বে, তারপরে ছবিগুলো দেখবে, তাতে যদি বুঝতে না পারো নেক্সট ক্লাসে আমি আর একবার ডিসকাস করে দেবো। আচ্ছা, তো now we know that this is the frequency. Now we are in a position to write down the final solution. Final solution means this equation 1, what is the form of this equation 1 after applying these boundary conditions. So let's see. So the final solution is given by yn. This is for nth mode, obviously. So d2n sine omega n x right. So this is the form, and I have added nth suffix to every variable or parameter over here to denote that this is specifically for this kind of mode. N equal to 2, n equal to 3, 4, 5 or something else. Okay. So what I can do, that I can combine this d2n. We can take this d2n and multiply with these two, right? Take it into the bracket, and we can name this constants, merge this constant and name this something else. Okay, so I'm going to do that. So just, it is sine n pi x by L. Obviously, I have put the value of omega n over here, and then it is a n cos n pi ct by L and plus b n sine n pi ct by L. Okay, so this is our y, and this is kind of our general solution, but we can again simplify this, and just take this an is equal to some cn cos theta, and then bn is equal to cn sine theta. We can put this, and this kind of treatment we have already done in our superposition of SHMs. Okay, so I'm not going to show you that how it is done, because if you have noticed the calculations over there, you will understand that what is done over here. So this can be again re-simplified. Okay, and I can write it as, so the general solution y is actually summation of all the modes. Okay, so superposition of all the modes, so we can take n equal to 1 to infinity. Okay, so this is summation of n equal to 1 to infinity, then sine n pi x by L, so n cos Okay. So now I hope you have understood that why I have written like in suffix to every parameter, because that was for a particular mode, and when a wave is generated, I don't know how many modes are there, so the total displacement is basically sum of the displacement of every individual mode. So that's why I have added them all. Okay, and this is n equal to 1 to infinity, and this will give you the final displacement of the string. Now it can also be written as yn is cn sine n pi x by L cos n pi ct by L minus theta n. Okay, where we have taken cn square is equal to an square plus bn square, and tan theta is equal to Bn by An. So just take just what we have done. So here in the place of An, we have taken this Cn cos theta and Bn Cn sin theta. So we have replaced this, applies this trigonometric formula, and we get this. Okay, so this is the form. It's Yn. Uh, okay, so it's already 11 over here. So the next day, I'm not, stretching the class today. So only two, three things